You got it? I'm just teasing. You can't see the record button when you're sitting there, so it's just a rude thing I say to be annoying. It sounds very insulting for anybody who's not there. It seems like, how could you not see the record button? Well, you can't see the record button when you're sitting there. Like, you just can't. It's outside your field of vision. So it's kind of like when I used to teach calculus in Harrelson Hall to start with. Well, Harrelson Hall used to have these chalkboards that were really, really short rooms that like really wide. And if you sat way over there and the teacher's writing over there, there's actually sort of like a place on the chalkboard where you can no longer see. So there's like kind of an event horizon if you sit too close to the board way over there. So most of our rooms, the desks are far enough back from the board you don't experience this. But there's a few rooms we've got row of desks like right up here, which is just dumb. But anyway, I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you that we don't have to rely on our own righteousness, that we can have your righteousness if we just accept you, Lord. And we thank you that you're a good and gracious God, that you've allowed that. We just pray in your precious holy name that you'd glorify, that we be glorified in what we do this day, Lord, and that we would have clarity of thought. Lord, in your name I pray. Amen. Okay, so first order of business here, I'm just going to say just a little bit about block multiplication. So what's block multiplication? Well, in a nutshell, what happens is that if you have a matrix and it matches another matrix in such a way that the breakdown of these submatrices is like sort of matching. In other words, such that these products over here make sense, then you can multiply a matrix of matrices by thinking of the submatrices as numbers themselves. Like this is, fine, whatever. Let me get to an actual example. Here's one. So you could have these two 2x2 matrices, right? R of theta and B of gamma, cosines and coshs and sinches. And you could construct these. These are called block diagonal matrices. This is a 2x2 matrix. That's a 2x2 0. This is a 2x2 0. This is a 2x2 matrix again. So we're looking at a 4x4 matrix, which is made of gluing, four 2x2 matrices together. The neat thing is, when you multiply these kinds of block diagonal matrices, you end up getting the product of the diagonals plus 0. See, because what you do is you take this and times that, just like you've been doing with numbers, except these are matrices. These are 2x2 matrices. And like over here, the reason there's 0 plus 0 there is if I take this times that, I get B gamma 1 times that 0 matrix, this 0 matrix times R of theta 2, which is why I have 0 plus 0 here. So just to summarize, block multiplication, what block multiplication says is if you have two matrices with blocks which are consistently sized, all right, then you can treat those blocks like they're numbers and you just multiply the matrices in the natural way. This is called block multiplication. In particular, if you take the product of block diagonal matrices, where the block diagonal matrices, where the diagonals have the same size, then the product of two block diagonal matrices is just, you just multiply the blocks. So here, let me just give you a specific boring numerical example so that we're not so lost. If I take 1, 2, 3, 4, and then I've got 0, 1, 1, 0, this matrix, right? And I multiply by itself. So I'm saying these are zeros that I haven't written, so I'll write them in. So the off-diagonal blocks are not square, are they? They're rectangular, right? I've got a 3x2 that I'm just writing, and up here we have a 2x3. So you can multiply these two matrices, and what you get is actually 1, 2, 3, 4 squared, 0, a 0, and over here you get 0, 1, 0, 0, 0, 1, 0 squared. That's what the block multiplication does. See, because when I take this times that, excuse me, when I take this, the first column times, these two blocks times these lower two blocks, I get this. I'm going to use some color coding here. Explain. So I get this times that. That's 0 plus this one times that one, which also gives me 0. So this, of course, is the pink is what? We're looking at a 3 by 2. What's the corresponding block up here? 2 by 2, right? So this pink 0 is actually the 2 by 2 0. And just to make sure the counting makes sense, this is a 3 by 3, right? And we're multiplying it by this, which is what? Yeah. Oh, so by now you should have picked up on the, well, one of these, something I've written here is obviously wrong. Can you spot it? It's pretty obvious. What did I just say? I said a 3 by 2 times a 2 by 2 is a 2 by 2. Does that make sense? No. This is a 3 by 2, which is good because we're adding those together, right? So this is the neat thing, is if you can break a matrix up into blocks, you can subdivide. This is yet another way to the sort of subdivide matrix multiplication into a bunch of smaller matrices being multiplied, right? We looked at the column by column rule. That's a similar flavor. This is something in between, like column by column and row by row. It's something deeper. Yeah.
So when you're working with a zero matrix, do you have to keep in mind what the dimensions of that matrix are? Since, like, do you have to keep that in mind if, you want to work that with other matrices, or
right.
work that with other zero matrices?
Yeah, we do have to keep in mind how big the zero matrix is. I mean, if things are set up right, it takes care of itself, You can't do like allowed calculations and somehow get to something that doesn't make sense. I mean, garbage in, garbage out, so to speak. What is the square of 1, 2, 3, 4? It's 3. Oh, wait a minute. 7. You guys tell me. 7. I can't do math. This is sad. I need to write it out. Sorry. This is pathetic. I need to write this out. So here's 1 plus 6 is 7. And then I've got 3 plus, what do we got? 3 plus 12, 15, right? 2 plus 8 is 10. And 6 plus 16 is 22, right? So that's that block. This lower block is easier. It's 0, 0, 1. And you got zeros. Of course, if we look at the cube, then that lower block is going to cube to 0 because that's our token standard nilpotent matrix order 3. All right. Here's another example of block multiplication ideas. This one's a little bit more sort of what's the word? Abstract, in the sense that I'm just taking arbitrary square matrices A, B, C, D. I mean A, B, and C. All right. So these are square matrices, and I think I'm assuming that they're the same size. All right. So square matrices, same size, and I want to assume. I've assumed what? I've assumed that. Well, I'm asking, actually, I guess I'm asking the question is what conditions do I need for M formed by the blocks A, B, 0, C to be invertible, right? So I propose that the inverse we can also write in terms of blocks, which we don't know yet, D, E, F, G, and I just multiply it out. So the block multiplication, again, it's just like they're numbers, but you got to be careful to make sure that they stay in the same order. But otherwise, just what you already know. So I multiply that out. For that to be equal to the 4 by 4 identity, the 4 by 4 identity is the identity block. And so that gives us 4 equations, 4 matrix equations. I need that AD plus BF is I need that AE plus BG is 0, I need that CF is 0, I need that CG is I. Aha, well this right here says that's non-negotiable. This tells me that I need that G is the inverse of C. That tells me that G has to be C inverse. Once I know that G is C inverse, I can put that over here, and that tells me how to solve for E, right? That's going to tell me that E is minus A inverse BC inverse, actually, like I finally got down here. And then I think I can solve, I still need to figure out what F is. Well, since C inverse has to exist, if I multiply C inverse on both sides here, that will give me that F has to be 0. So in fact, the inverse of this block, this is an upper block triangular. There's yet another term you could learn. That's not upper triangular because it could be that the A and C blocks have numbers below the diagonal, actually, right? But it's kind of, it's an upper triangular, you could say. Anyway, here's the derivation that the inverse of such a matrix is given in terms of blocks, in terms of block inverses like that. Okay? So this in a nutshell is block multiplication. Sometimes we use it, a lot of times we don't. It's something you should be aware of, that's all. I give you, like, there's a token homework problem you have about it. I thought that I should have the decency to talk to you about it for 10 minutes before you have to turn the homework in. Yeah. Of course, you could have read the notes. You didn't really have to wait for me. But, or you can ask me in office hours. You have many options, right? Now, the real reason to think about blocks is actually more appearing in the next chapter. The next chapter, we're about to talk about Gaussian elimination, all right? The number of steps for Gaussian elimination depends on the size of the matrix, and I'm a little rusty on this, but I think it depends on n squared. But anyway, or you might calculate the determinant of a matrix, right? The determinant of the matrix, we don't know what that is yet, but whatever it is, it depends on like n factorial. So if you've got a you got a 3 by 3 matrix, we're talking about 6 factorial. Oh, okay, fine. 4 by 4 factorial is 24. 5 by 5 matrix, how many arithmetic steps to calculate the determinant? 120. 6 by 6, 720, you know, and by the time you get to 10, the number of arithmetic steps to calculate the determinant without tricks, it gets to be quite staggering, right? On the other hand, to calculate the determinant of a submatrix that's 5 by 5, well, that's just 120 versus that ginormous number for 10 factorial. So if you can take your matrix and you can chop it up into blocks, you can do numerical methods on the blocks much more efficiently if you can identify some like 0 matrix that you don't have to work on. So blocks are important for MATLAB and other things. They're behind the scenes. It's how we get some calculational efficiencies, is breaking systems down in terms of blocks. Okay. But anyway, there are other reasons to like blocks, but I will now put this away because I want to work on the next thing slowly. Oh, any questions? Yep. The transpose, yes. So I think the easiest way to do is just look at an example, right? So if I had, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, since I'm being lazy. So if you want to think about that matrix, take the transpose, what happens? The first row becomes the first column, the second row becomes the second column, you know, it's transposed, of course. So this is the definition of transpose I'm doing, right? So what happened? If we, let's give some names here. So suppose this is my A, my B, my C, my D. What are the, after we transpose, what do we got? That's a transpose. This down here, look at it, it's just D transpose. And how about, what happened? The off-diagonal blocks, they did what? They switched and they transposed, yeah. So this is actually C transpose B transpose. So it looks like, at least for square block decomposition, and if I had to guess, I think this probably generalizes, that this is exactly A transpose, C transpose, B transpose, D transpose, like that. Now, if I wanted to go prove that sort of thing in general, I probably would appeal to the notational scheme I have at the start of this section in terms of those mixed indices and my sneaky notation. That's a little bit off the beaten path. You know, if I was teaching a course which was just on matrix manipulation, I'd probably get into that. If you want to go deeper into this stuff, there's a book by Gullub which goes very deep in these sorts of ideas. But that's beyond this course. So you can get you can't. I mean, it's only available in India or East Asia, but if you go to the right website, you can buy it here for about 20. Well, 10 for shipping, I don't know. So, okay, so I think that answers your question. That's certainly all you need to do that homework problem. Yeah, more importantly, yeah. Okay, so let us begin our discussion of solving linear equations. Let me start out with a basic example. Suppose I've got x minus y equals to 2, and I've got x plus y equals to 8. I want to solve these two equations and two unknowns. How do I do it? Well, you may do it different ways, but here's how I do it. I take these, I add them. When I add these equations, adding both sides, that gives me 2x equals to 10. Therefore, x is equal to 5. Right? And then you can pick either one of those. Pick either one of those to go back and solve for y, right? By using equation 2, we have y is equal to 8 minus x, which is 8 minus 5, which is 3. Therefore, y is equal to 3. By the way, what's the solution set? It's kind of obnoxious, but it is a set. A set. So it looks like, it's kind of boring, it's 5, comma 3. So there's the solution set. The solution set is a set which contains all your solutions. I'm saying this because I asked for solution sets in your homework and I want solution sets. If you just box 5 and 3 like that and you leave it, we will take off points because that's not what we asked for. A set is a set. Okay. You have been warned. So the larger point here, though, is what did I do? I mean, what's this idea? I added these equations, right? And that was enough to solve it, right? It eliminated one of the variables. Example 2. And the other thing that wasn't, I was a little bit vague here. I should really have told you over what number system we're doing. I could have said over the reals. I mean, I could have said over the rationals, Okay. Let's see here. How about if we have 2x minus y plus z equals to 2, and x plus y plus z equals to 0. Suppose we want to solve this, again, over the reals. Keep it real for a minute here. I could say the rationals, it wouldn't change anything. So here, what I find it, I mean, there's various ways you could go here, but one thing we could do is we could multiply by 2, right? So this gives me 2x plus 2y plus 2z equals to 0. Multiply by 2, right? Multiply by 2. And, of course, the first equation is still what it is. And then I can go back to my, my idea about adding or subtracting equations again, right? Like I can subtract these equations now, and what do? Well, I'm not going to add this time, I'm going to subtract, right? So subtract the lower equation from the top equation, what does it give me? The two x's cancel, right? And we get what? We get minus 3y plus z equals to 2. Yep. Oh yeah, thank you. Much appreciated. So look at this. I can solve for y. Y is equal to, 2 plus z divided by 3. What's not entirely obvious is that's as good as you can do. I can go back. What's x equal to then? Did I miss my minus? Oh, yeah, minus 3. Thank you. And how about x? Let's see here. X is equal to minus y minus z, right? Which is actually 2 plus z divided by 3 minus z, also known as 2 minus 2z divided by 3. What's that? There are many opportunities for making mistakes here, are there not? Yes. Fortunately, it wasn't me this time. So the solution, I mean, not yet anyway. Solution set, pride goeth before the fall. Solution set would be x. What is x? It is, I'll write it as 1/3 of 2 minus 2z, right? What's my y? My y is minus 1/3 of 2 plus z, right? What is my z? What's z equal to? Just z. Very good, yes. And z is what? Any old real number. That's the solution set here. Now, I think example 2 is a little bit unsettling in the sense that you have this, like, when you're done with this one, you're done, right? You found this unique solution. You have the sense of completion. Like, you can tell it's done. Over here, you see I had other flavor choices, right? Like some of you might have found it more natural to solve for z in terms of y, right? I could have also written this solution set in terms of y being a free variable, right? Our default setting in here is to use the last possible variable as the free variable when we do the next thing in here. So that's why I did it this way. So this procedure I'm doing, there's a better way of doing it, and the better way of doing it is to use what are called row operations on the augmented coefficient matrix. So let me introduce those, and then I'll revisit these two examples using Gaussian elimination. All right? So first of all, a definition, which I might have stated before, but I'll state it again at the risk of being redundant. If we have a11 x1 plus plus a1n xn equals to b1, a21 x1 plus plus a2n xn equals to b2, and so forth and so on. am1 x1 plus plus amn xn equals to bm. So what I'm looking at here is m equations in n unknowns. What are the unknowns? x1, x2, xn, right? the coefficients, and we have to talk about doing this over what's called a field. So the a sub ij's, these are going to be taken from F, some field. Okay. So this F, basically there's almost always in here, it's going to be the real numbers. Sometimes it'll be the complex numbers. At the start, just to show it's possible for you guys, I'll sometimes take it to be a finite field, which is just Z mod a prime. All right? So I have a token few problems in this course about modular arithmetic because I think it's important for you to be exposed to that. It makes it less weird when you get to the next course and are doing it all the time. It's not your first time seeing it. You've seen it here already. But the majority of our effort will be spent on the reals. And of course, you could also put, you math majors will like this, the rationals, right? Those are our usual choices for the field. Those are our usual choices for the coefficient and also for where the unknowns are coming from, right? The B's, these guys right here, these are the inhomogeneous terms. All right. You can group them together as a vector, right? And if that vector is equal to 0, then system is said to be what? Fill in the blank. If the inhomogeneous terms are all 0, the system is a what? Singular? No. Actually, homogeneous system. So if there's even one equation where the b sub I is not 0, then the system as a whole is inhomogeneous. The solution set is the set of all x1 xn. What's the solution set? Let's just write it out in sort of words for a second here. Solution set, what is that? It is x1, x2, xn, such that what? This vector solves star. Let me give this whole thing a name, star. All right? So it's the set of all tuples, which when you plug them in, they simultaneously solve not the first equation alone, not the second equation alone, not the mth equation alone, but all of them at once. Simultaneous solution. Now, of course, as we have seen, you can rewrite this as the coefficient matrix A, right, times the vector of knowns x is equal to b. Or sometimes I'll use a v for that x. I don't always use x. I mean, you might, I'm calling this thing x in the statement above, basically, right? That's the matrix statement of this system, right? We have m equations, or we have one matrix equation. It's pretty nice. But nicer still, of course, this is the coefficient matrix, right? Again, this is the inhomogeneous term. And then we get the coefficient, the augmented coefficient matrix is A, would be like this. This right here is the augmented coefficient matrix. So let's think about this. We have this system of linear equations, right? What things can we do to this system of linear equations that don't change the system? And when I say don't change the system, what do I mean? I mean they don't change the solution set. Gaussian elimination, yes, that's the ultimate answer. But let me just take a step back here. What's the augmented coefficient matrix for this?
1
minus 1, 2, 1, 1, 8, right? And if you look at this, if you use your imagination a little bit, what's the augmented coefficient matrix? I mean, to be clear, I also should say, and by the way, x plus y equals to 8 is, or maybe I should say, well, I don't know, I guess I got to decide what I'm going to say. Curses. I got to keep one of the equations or the other. I mean, there's still two equations, right? So I don't know which one I'm keeping. I'll keep the second one. This is really little interpret. My point is the first equation, 2x equals to 10, corresponds to this row, right? 2. Well, let me write it second. How about that? Sorry. I'll get with it eventually here, guys. Let me do a little interpretation here. Let's say that we're taking these two equations for really x minus y equals to 2 and 2x equals to 10. Okay? Just to be. So I'm just leaving the first equation alone. I'm replacing the second equation with the sum of the two equations, right? So the augmented coefficient matrix, essentially after adding the equations, is really 1, minus 1, 2. Left the first one alone. But the second one, I've got 2, 0, 10. So you see what happened really is you could think about this process of adding equations just in terms of adding rows, right? This is the insight of Gaussian elimination, is that, and then over here, you know, if you want to think about it, my initial augmented coefficient matrix was 2, minus 1, 1, 2, 1, 1, 1, 0. And what I did was I multiplied row 1. I did 2, I'm sorry, what did I do? Not row 1, what did I mess with here? Row 1 or row 2? I messed with row 2, right? So in the augmented coefficient notation, I can say that's 2 times row 2. That's my new matrix. So that is 2, minus 1, 1, 2, 2, 2, 2, 0, right? So multiplying a row in the augmented coefficient matrix corresponds to multiplying one of your system equations by a non-zero scalar. That does not change the solution set. Adding equations does not change the solution set, right? What else can you do that doesn't change the solution set? Yeah, and we can interchange them, right? It doesn't, like, you could have told me, over here it's kind of silly, but you could have said, well, this original equation, it's really x plus y equals to 8 and x minus y equals to 2, right? So that would have augmented coefficient matrix 1, 1, 8, 1 minus 1, 2. See, this and that are different, right? But those represent the same system of equations. It's just a relabeling which one came first, the first equation or the second equation. So these are the three things we can do to an augmented coefficient matrix and not change the solution set. These are called elementary row operations. All right? The game we play with Gaussian eliminations is to use elementary row operations to manipulate the matrix into what's called reduced row echelon form. All right? So I'm going to show you guys some examples of that. But first things first, definition. Elementary row operations. So type 1 is to interchange rows. Type 2 is to multiply row by non-zero scalar from your field, whatever field you're working over, be it reals or rationals or complex or, you know, modular, not a prime, a finite field. And then type 3 is to multiply both sides of equation I by C and add to equation J. So type 3 I have illustrated in either adding or subtracting. But you could also think about it, you could also take one of the equations, multiply the other, take one of the equations, multiply it by 3, and add it to the other equation. That would not change the solution set either. I've just added equations or subtracted equations, but you could add multiples of one equation to another. That's the type 3. In both of my, and everything I've done over here, C has been equal to either 1 or minus 1 so far. All right? So, let me illustrate the Gauss-Jordan algorithm. Well, you know, there is a systematic, careful, non-debatable, certified by someone who has a serious background in computer science algorithm in my notes. That's my brother. He's half, you know, I'm half physics, half math. He's half computer science, half math. Well, I mean, he may be a little bit more than half math at this point, and so maybe I may be. But at one point, we were 50-50, math, computer science versus math, physics. And so the algorithm you find in the notes, if there's some sort of logical flaw in that, if there's some sort of endless loop, it's his fault. So anyway, so let's start here. 1, 1, 8, 1, minus 1, 2. And so I'm also going to be, rather than stating the algorithm, which would be not helpful, I'm going to show you examples which illustrate. My examples are not even going to illustrate the algorithm, though, actually. They're going to illustrate the algorithm paired with arithmetical laziness. The algorithm is not afraid of fractions. I am personally afraid of fractions. So I'm afraid of doing fractions in class. Let's just say that. R2 minus R1, that's not entirely true, but I avoid fractions. R2 minus R1, this means row 2 minus row 1. And the system, the nomenclature here is that the first row that I write is the one I modify. So 0 looks like minus 2. Looks like minus 6, right? And let's see, next step I might make would be row 2 divided by minus 2. At this point, I have completed what's called the forward pass. This matrix actually is the REF of AB. That's the row echelon form of AB. Excuse me. There's another thing I should have told you guys, is if you take a matrix A and you do any of these three to a matrix B, 1, 2, or 3, any of these guys, you go from matrix A to a matrix B like that, then matrix A and B are said to be row equivalent. You can prove that this is in fact equivalence relation. It's symmetric, it's transitive. Any matrix is related to itself. But these are called row equivalent matrices. The idea being, of course, that row equivalent augmented matrices share the same solution set. That's what I was motivating up to this point. So anyway, that 1, 1, 8, 0, 1, 3 is row equivalent to my initial matrix here, right? But we're not done. This is not the reduced row echelon form. So the next move is to take row 1 minus row 2. So now I'm messing with row 1. So I've got 1, 0, 8 minus 3 is 5. 0, 1, 3. Now we're done. So these are both pivot columns, right? There's only one column that's not a pivot column. The third column is not a pivot column. It does not have a leading entry of 1. And of course, this is what's known as the reduced row echelon form of AB, or the REF. We can read the solution set to the system unambiguously from the reduced row echelon form. I mean, this augmented coefficient matrix is equivalent to what system of equations? 1 times x plus 0 times y equals to 5. 0 times x plus 1 times y equals to 3. So apparently, x equals to 5 and y equals to 3. What do you know? All right. By the way, is this the right way to solve this system? I would say categorically no. This is absolutely the wrong way to do it. The right way to do it is the way I did it at the start. Add the equations, plug into the other variables. It's a 2-by-2 system. Gaussian elimination is dreadfully slow. Where Gaussian elimination starts to pay off is for problems like this, which start to be where you're not comfortable with what you're doing. So here's the augmented coefficient matrix to start with, right? And I've already gone off the beaten track in terms of the standard Gaussian elimination by multiplying by 2. All right, standard Gaussian elimination would do something like subtract 1/2 row 1 from row 2. Instead, I multiply them both by 2 so they match up. Now, see, I'll go on though. So next move. So then you identify the leading, basically as far up to the left and high as you can get. You want to make that non-zero. You identify that as your pivot. Then you want to clear out below the pivot. So the way I'm going to do that is row 2 minus row 1. So that means minus that row 1 gets left alone. What happens when we subtract row 1 from row 2, though? 2 minus 2 is 0. 2 minus 1 is what? Oh, 2 minus a minus 1 is 3, right? 2 minus 1, 1. 0 minus 2 is minus 2. All right. Then my next move would be to, I guess I'd take row 2 divided by 3, just to make the math a little bit easier to. I mean, you could do fractions and stuff here, but I'll go ahead and do that. What I'm trying to get at, guys, is this is a way to do it. It's not the only way. Yep. Oh, yeah. Most appreciated. I really hate to get that comment in 2 minutes from now. Thank you. Please jump in when I do these sorts of things. We all thank you. So then my next move, okay, at this point, so the initial pivot position is the upper 2. At this point, this is my, my next pivot. And now I'm pivoting on 1, right? So I want to get rid of everything above it. So what I can do is row 1 plus row 2. That's going to give me 2, 0. 1 plus 1/3 is 4/3. And 2 minus 2/3 is 4/3. And I've got 0, I've got 1, I've got 1/3, I got minus 2/3. Right? To finish the Gaussian elimination, I still need to rescale my first column, row 1 divided by 2. So I got 1, 0, 2/3, 2/3, 0, 1, 1/3, minus 2/3. This is now the reduced row echelon form of the initial matrix. So it's in reduced row echelon form when you've done row operations until you have, you have pivot positions which have been scaled to 1, and you have zeros above and below the pivot 1s. And you want the 1s to be as high up in the matrix as possible. You always want to have sort of a a stair step of 1s down from the top. That's echelon means stair step. Reduced stair step form. Now, this is as good as it gets. And by the way, what does this equation mean? This means that x plus 2/3 z is equal to 2/3, right? And this means that y plus 1/3 z is equal to minus 2/3, which is to say that x is equal to what? 2/3 of 1 minus z, and y is equal to 1/3 of, anyway, let me stop factoring stuff out. I'm an idiot. X is equal to 2/3 minus 2/3 z, and y is equal to minus 2/3 minus 1/3 z for any z. And isn't that what I have over here? This is my x, right? This is y. Z is free. See, the reduced row echelon form will conspire to make the last variable the parameter in the solution set in as much as is possible. Now, if you've never done this before, if you've never done row reduction in your life before, there is no earthly way you can learn it from me in 10 minutes, or 20 minutes, or if I spend the next 2 weeks showing it to you. There is only one way you can learn it. You have to do it for yourself. Now, you are not alone. In this age of blessed technology, there is a wonderful, wonderful help on this topic. And so if you, I might have the link in the course webpage. I forget where I put it. Oh yeah, useful materials and links. So the top one calculates the roof and more. So here we go, transforming a matrix to reduced row echelon form, which is what we're just doing. That is Gaussian elimination. Let's look at a bigger example. Let's do 4 rows and 8 columns. Let's get nuts. So I don't know. Oops. All right, there you go. That's an example. And not only does it do it, it shows you step by step how Gaussian elimination works. So according to the standard thing, you take the first matrix, you add -1, the first row to the second row. See, he's pivoting. He's pivoting on the 1. He's taking that, making that 0 by adding -1 times the first row to the second row. Then what does he do? He -2 times the first row to the second row. Then he sweeps that 0 out under the first pivot position. Then he creates this 0 by adding -6 times the first row to the fourth row rather. At that point, we've finished with this first pivot position, and he's going to move on to the next one. Next time, he's going to take this one, and he's going to try to create zeros under it. Next thing he'll do, he'll be adding row 2 to row 3 to create a 0 here. See that? That's what he did. And then what? Then he added 6 times row 3 to row 4 to create a 0 there. At that point, you've swept the zeros under the second pivot position, so you go on to the next. Look for the next non-zero column right here. That's going to be your next pivot. You got to get zeros under it. So what you're going to do, you're going to add 6 times the third row to the fourth row. That's what he does. See that? 6 times the third row to the fourth row. There it is. And then at this point, that's going to make that your fourth pivot. So he divides by 24 to make it into a 1. this is the REF, and then what's he going to do? He's going to do the backwards pass, which means he's going to subtract copies of row 4 to get rid of this 3, 4, 4. He's going to subtract copies of row 3 to get rid of this 1 and 3. Then he's going to subtract copies of row 2 from row 1 to get rid of that. And at the end of it, he's going to have E1, E2, E3, and E4 for his first 4 columns. And there's some arithmetic. But here it is. Pivot column 1, pivot column 2, pivot column 3, pivot column 4, and the non-pivot columns. If this corresponded to 4 equations and 7 unknowns, you would be writing x1, x2, x3, and x4 in terms of x5, x6, and x7 as parameters. So I don't think your first mission even requires you to learn Gaussian elimination, so relax. I just gave you linear systems that you have to solve. You can solve them by whatever method is most natural to you, by elimination, adding equations, etc. If you want to try to do Gaussian elimination, you can, but you don't have to. I didn't ask you to do that in the first mission. The second mission, though, I asked you to use Gaussian elimination. But you don't have to be a robot. You don't have to do it like this. You can do it like I did, which is not, you follow the spirit of the algorithm, but not the exact algorithm, yeah? So anyway, I shut up. Thanks, guys. Yeah.
Is it pretty much just like you're doing things in hope of that, and after you do it a lot, you'll start to recognize it? But at first, you're just kind of like manipulating it in ways that you think it would work?
Well, you have to